our speaker today, Iwan, sorry, just admitting people, Iwan Sanja. He's an assistant professor in computer science at the College of the Ozarks, where he teaches computer science courses in programming, data science, computer vision, and I think other areas of computing sciences. And he brings to his teaching his background in computer vision, programming, and software engineering, and integrated hardware systems, among other things. So yeah, thanks for being here. And yeah, great to have you and look forward to hearing what you talk about.
Thank you, Noah. Thank you for the introduction. So I will start by sharing my screen, and forgive for my background, but that's have meaning later in the presentation. So I will explain later about that one. So I will share my screen. Okay, I hope all of you get the IPython notebooks and can follow along. And yeah, if you want to be interactive by chatting, put something in the chat, ask questions. I don't mind if you interrupt me with questions so I can explain directly. At the end, I will give times also for question and answer. Okay, so the topic of today is introduction to particle swarm intelligence. Since 1960, there was a trend to imitate living beings for solving such kind of hard optimization problems. And this trend is continuing up to now. The umbrella terms is evolutionary algorithms, including genetic algorithms, evolutionary programming, and evolutionary strategies. Today, we will focus on particle swarm optimization, introduced by Kennedy and Eberhard in 1995. The idea is try to simulate bird of flocks or fish school, and then try to imitate their behavior with simple rules, and then we will see the emerging behavior out of it and apply it to the search problems. Instead of solving it with mathematical formulation and formal methods, we will use this kind of meta heuristics methods to find out the optimum value in a function. Why swarm? Why we will use swarm? Because there are several reasons. First, if we see swarm, they are when they only use a single, let's say ants, single ants looks like powerless, right? Looks like they are very simple, following simple nature. But if there are swarm of ants, then they will become powerful. We in computer science imitate, try to observe ants, and then we have ants algorithms for path findings, and then the Bible also says since old times, like you, sorry, I'm from Texas, you slackers, go to the ants and observe and look their behavior and learn from them and be wise. And this one inspired us to do more research in particle swarm optimization. So here is the swarm of birds. They can fly without hitting each other. And then flock of fish, for example. One of the things also, when you flock like this one, then you have more power against the predator. And then they can, the predator sees like they are just a background, for example. And then for finding food, because they have, they do it in swarm, communicate with each other so they can find food much more faster. So we will try to do that one in solving optimization problems. let's start with Rosenbrock banana functions, non-convex function introduced by Howard Rosenbrock. The plot of Rosenbrock function has a minimum value at 1.1. So here is MATLAB, Matplotlib, similar with MATLAB. If you are familiar with MATLAB, the transition from MATLAB to Matplotlib will be like smooth. So I will import all the library that I needed, and then I will set the figure size, and then I will have a subtitle there for the plot, the search area, and then for the first plot, I will make the data from -3 to 3 with space 0.05 for both x-axis and y-axis. And then after that, I will create the mesh grid, x and y. So all the intersection point between x and y value on the bottom. And then I will have the Rosenbrock function here. So the Rosenbrock function is quite easy, 1 minus x squared plus y minus x squared, parentheses in parentheses, and then square. So using that function, I'll calculate the c value, and then after I have the c value, I will plot the surface. Okay, and then I do some customization to c-axis to format the numbers so it will look nice, and then add color bar to see the meaning of the color. And then I have second plot. In the second plot, I use wireframe instead, so we can see what is the function. So if we run this one, we will see two plot in here. Okay, so in here, in 1, 1 is the lowest point. So our goal is to find out the lowest point. Okay, let me continue with the next one. So the next one is now I will plot the contour. I will project everything to the bottom space, and then see the contour there. And then I also have a contour plot. So if I run this one, so we will see something like this one, right? So if I project, so this one is assume on the very top here, I will have up to 160. In here is just 35, and then you can see the contour there. So I projected the contour to the bottom floor, and then from that bottom floor, I put it in this plot. Okay, and yeah, we call this one is contour plot because the same line here indicate the same height. Okay, and by the way, this one is reminds me of Pagi Tires in Bali contour plot, and that's one of the architecture works also. So to find out the contour in here, we will use like simple technology like A-frames with thread and rock, and see if it's same height right in the middle. So we will draw lines and continue. So we can have the contour there. Okay, so using this contour plot, now I will try to find out the lowest point in here. Okay, so this one bring us to the particle swarm or algorithms, right? So this one is the gist of particle swarm. I will try to particle swarm optimization algorithms. So I will try to explain this one in much more simple term later, but we will go through the formal way first, and then I will give you more illustration to see what is particle swarm. So first, we similar like the other algorithm, evolutionary algorithms, they will start with a population of particles. population of particles with random position and velocity on D dimension in the problem space. And then for each particle, evaluate the optimum fitness function in D variables. So we try to evaluate, for example, this one is our search space, and then we will put random particle here, and for each particle, I will evaluate what is the value there. Okay. And then I will compare the particle fitness function with the particle personal base, P base. So in here, if the current value is better, then set the P base value equals to the current value, and the P base location equals to the current location in D-dimensional space. And then I will compare the particle fitness evaluation with population overall previous base. So in here, I will compare with global base. So every particle will communicate to each other, telling each other, oh, here is my personal base, and then they will compare, and then they will come up with the global base. Okay, so we have personal base and global base. They can be the same point, but they can be also different point. And then next is the updating the velocity and position. For the velocity, we have three terms here. The first terms is the inertia, because I am going to some direction right now, right? And then based on the physics, Newton's law, if I move to that way, I will keep move that way. I don't want to change my directions. I will stay on my path. The next one is the personal base, a vector from personal base with my position right now. So that one is a vector pointing to my personal base, to my personal base in my experience. So I already searching and collecting, and then I found out, oh yeah, this is my personal base. So I remember that one, and then try to have a direction, try to move toward that direction. And the last part is personal global. This one is not personal, but global base minus my position right now. So this one is vector pointing to the community global base. So after I ask everyone in the neighborhood, I know, oh yeah, they said my personal base might be different with the one that they have. So I also have that vector. So if I sum all these three vectors, then I will have a new velocity. After I have the new velocity, I will update my position based on the new velocity. Okay, and in here, if you see there is constant 1 and constant 2, constant 1 and constant 2, you can set you can tune this one and set the value between 1 and 2. Okay, so this one is like giving a weight. Oh, I will prefer to following my personal base instead of community base. I would like, oh yeah, I will go. I will follow the crowd instead of just focus on looking at my own toes, for example. So you can adjust this value, and then they will. We can simulate and see what is the result. Okay. And then the last step is a looping. So go back to step 2 and keep looping, keep doing the same things until a criterion met, usually sufficiently good fitness or maximum number of iteration or generation. So I will do that one over and over up to the point, oh yeah, it's low enough, I can accept that result, or I reach the maximum iterations, and this is the best result after, let's say, 10,000 iteration. Okay. So yeah, here is another explanation. So you can imagine if we throw in here is like a hill, right? In here, hill, and then imagine there are 3 kids, for example, in the hills. Okay, as a modern kids, or let's say Boy Scout and Boy Girls, right? Boy Scout and Boy Girls, and they have a GPS or smartphone in their hands, so they can find that altitude wherever they are, right? And they can communicate with each other. So they try to explore, try to find the minimum altitude. Okay, and then they will remember their personal best. So when they explore, going down, going up, they will record the personal best and try to move to the direction. And everybody will compare their personal best, and then we'll have the global best. So that will give the vector to the global base. And then I have my own direction based on those 3. I can combine, and then I can update my position. So that's the simplified versions of the algorithms. So here is the vector global base. Here is the vector of personal base. Here is my own velocity. If I sum all these 3 vectors, will become the next velocity. Okay. So we try to implement that one in here. Before that one, here is yeah. Let me try. So here is the number of function of variables 2, because we have x and y as the variables, and then we will have initialize the position, random velocity for each particle. This one should be a 0 velocity, sorry. So I have position as a random number between -3 to 3. The NumPy random number generator will generate random number between 0 and 1. So I multiply by 6 and -3. The offset is -3, so it will become the maximum will be 3 and the minimum will be -3. Next is velocity is 0, and for personal best, right now my position right now is the personal best, and then personal best value will be 0, all 0, because the value right now initialized by 0. And then I will have the banana function. Try to calculate the banana functions, and then I calculate the global best, and then plot the contour, and plot the swarm with the global best with a red color, and then all other one with a green color. And I have interactive plot here, so you can try to simulate. This one is 51 particles, but you can change it into a lower one. This one is a 6 particle, for example. This one is only 3 particles. Okay, so they will try. So I will initialize the particle randomly, and we can decide how many swarm that we can use. Okay. The good things about particle swarm algorithms, nowadays the computer become more and more into the parallel processing, containing many cores instead of single core. So by doing this one, we can assign each particles to single core, and everything will do their own stuff, and then they communicate. So we can solve problems much more faster by doing this kind of things. So we can utilize, for example, if you have 10,000 computer in your organization, and they will not use it all day long, right? when they are in the night, for example, I can assign them as a swarm particle, one particles, and then they're doing the search and communicates with each other. Okay. So next part, by using the same code here, initialize the random position, zero velocity, personal best for each particles, and then for all the number of swarm, I will calculate the personal best value, finding the global best, setting up the animation and figure. I will have in here now the animate swarm with iteration, with how many number of iterations. In here, updating the personal best. So I have the current value, and then I will calculate using the banana function, find out the current value. If the current value less than the personal best, then I will update the personal best with current value. I also record the position. I will try to remember that position, put a marker on that position. Okay, and then the next part, updating global best. So in here, I will find the minimum from all personal best value. After I find that one, I also record the position, record the index, and then if it's less than global best, I will update the global best, and then the global best positions equals the copy of the position of the best index. Okay. The third part, the third step is updating the velocity and position based on the calculation based on the vector equation. So this one is velocity and then plus equal signs. That means I will maintain the velocity as the inertia, and then I will multiply C1 0.1 in here. I set 0.1, and then find the vector from personal best with my own position, with current position right now. Then the next part is I will multiply by C2. So this one is 0.2, random number with global best minus my position right now. So this is the third factor, the community goals, right? So in here, but I give more weight towards to the community goals instead of my own goals, my personal best. Okay. And then the next part is about plottings. I setting up the contour plot here and plot all the swarm with green, and the best position will be in red. Okay, and if I run this one, I think it will take around 1 minute, but it will generate a video and animations how the swarm move. If you have any questions, you are welcome to ask questions. Oh, it's more than 1 minute. I am sorry.
No problem.
Any questions while we are waiting?
So you said if you change, so if C1 is larger than, then the swarm will be more dispersed because the individuals will prefer their own
Right.
path.
So they will tend to find a local base instead of global base.
Gotcha. Okay.
So here is the result. Here is the final result, right? That's 1 and 1. So that's correct. But in here, we have a video here, and then we can run it in a loop, for examples, and run it. So you can see it will go toward the middles and try to find the minimum there. It's like a swarm of, you can say a swarm of birds attacking the food, foraging for solution here, right? Foraging for solutions and find out the best result. And yeah, you are welcome to change the parameter there and see what is the result there. And what's next, right? Activity and what's next. You can change the function into another function and see the result. That's another way. Another activity. The other one is modify the velocity equation to include the inertia weight. For example, in here I have W. And W will decrease linearly from 0.9 to 0.4. So we can change the code and update the code with a new formula and see what behavior we have. We can use swarm particle to model different behaviors of animals, insects, bacteria, or human cell. So there are swarm of possibility with the particle swarm optimization. So you can model social insects, right? How they eat the corn, for example, and try to simulate that one, see what happened. Or you can simulate blood cell in your vein and see how it will circulate through your body. In my research, we did also find insight from termite, for example. We try to simulate termite with simple rules. If I see a block of wood, I will take it, and then I will move randomly. And then if I see another wood, I will put it, and then take the next one, and I move randomly again. And many big companies benefit from this kind of simulations. For example, Southwest Airlines, they improve their transport by analyzing using swarm particles. And then Capital One, credit card company, they also survive because they apply a simple principle. The CIO, information technology, he implement 4 simple rules to adopt new technology, and that makes Capital One become from a small company become a big company. And then you can also visit these 2 websites if you want to learn more. There are tons of possibilities. There are many possibilities that we can do with swarm particles. We can try another simple rules here with predator, and then try to have a different kind of swarm. One is predator, one is the swarm, the regular swarm. and then see what happens, see their interaction also. Okay,
Yeah, I was gonna
yes,
ask
sir.
if so the banana function models that like local minima or the global minimum. So like in this case, you said the swarm kind of go toward that minima like a food source. So would a predator just kind of be inverting that so that it's a maxima and they'll like stay away from it then?
Oh, yeah, we can for example, so we are no longer limited with the optimization, but we just try to simulate their behavior. So the idea is from simple particle or dumb bugs, but because connected in big networks, they will become smart. There will be emerging behavior out of it. So that one more on the NeoSwarm. I can show you some of the website in here, NeoSwarm. And in here, let's see. Yeah, here is termites that I talk about, and there is a video also. They will take chips of wood and move randomly, and then they will stop when they see another wood, and then they will collect all the wood into one pile. So in here, we no longer have the contour plot, we don't have the terrain, but we just try to simulate a simple behavior, but collectively doing it together and see what is the emerging behavior. Is there something smart? Is there something that unpredictable that we can learn from doing from these animals, these social animals? Here is much more interesting because you can see the pattern. If they're eating the wood and give you the path to the wood, give you the pattern when the similar patterns you see every day when you have termite. Okay.
Neat.
Any other questions?
Well, if not, let's thank Yuan for a great presentation. Thanks.
You're welcome.
Yeah, appreciate you you coming out, or well, I mean virtually at this point, but yeah, so Chris and I will be meeting and discussing, and we'll be back in touch soon.
Thank you for the opportunity, and it's a privilege for me to present this topic.
Thanks a lot.
I spent like 8 years, more than 8 years, try to simulate this one and observe their patterns. So if you have any other questions, or you have something that oh yeah, I want to apply this one in my field, you can always send me email and ask questions. The next thing that interesting also is like genetics algorithms. Try to simulate mutation and crossover, and then they have like initial population, but doing the crossover and mutation will generate new offspring, and from the new offspring they will evaluate with natural selections, and then find the best for the next one, the next offspring, the next generation, and repeat the cycles. That's also similar optimizations meta heuristics method like this one, but also very powerful.
Mm-hmm.
Okay. Thank you so much, Iwan. Carrie, Josh, and Lisa, could I ask you guys to stay on for a minute so that we can discuss next steps? But Iwan, thank you so much. We will be in touch soon.
Okay, thank you. Thank you very much.
Have a good weekend.
Okay, so I thought